David is our other tutor. He's going to be on standby. So if you guys have questions, email David or Janelle. They should be like your first ones. We're going to hold off on questions till the end. So, if you have any minor questions, like quick questions, when we're doing the lecture questions, like the questions that Mark has prepared, when we're reviewing the answer, if you have a question that's quick, we can go over it during then, but any main questions we'll be taking at the end. That way we can kind of streamline this and make it as as efficient as possible for everyone.
So like I mentioned, when I'm doing the poll questions afterwards, if you guys have a quick question about this question specifically, go over it. If you have more in-depth questions, please hold off until the end, or email or private message one of the tutors. Okay, and the tutors are going to be the co-hosts or hosts of this meeting, so you know who to email. Okay. But without further ado, let's see if we can get started on lecture. Okay, can everybody see my screen?
Yep. Yes.
Okay. So for anybody who's joining us for the first time, my name is Mark Abdurrahmanov. I'm a recent graduate of Stony Brook University. I just received my Bachelor of Science in Biochemistry this June. My MCAT date was January 16th of this year, so only a couple months ago. I scored a 520, and you can see my score breakdown. This is my email if you ever want to contact me with any questions or topics. So before I get started, I want to talk briefly about this course for anyone who doesn't know. It's a 15-week full course. Again, it should have said started last week. I didn't change that. There's 3 lectures per week: Thursday, Friday, and Saturday. Okay, so this is the first of this week, the first lecture of this week. Now we're doing 1 office hour per week on Sunday at 8:30 p.m. Eastern Standard Time, but the day and the amount of office hours may change. And all lectures will also begin at 8:30 p.m. Eastern Standard Time. We'll cover most of the highest yield MCAT content over this 15 weeks. Okay, it'll include basically almost all of the topics that are in the MCAT. There's a few very specific ones that we may only briefly cover in one lecture or not at all. But if you see those, please feel free to come on office hours to talk about those. Okay. All right. So we also have a GroupMe. The link is right here. The GroupMe will have all the lecture recording links and PowerPoints posted. So it's a one-stop shop for everything with the lectures. We'll also be posting any updates or changes to scheduling there. If you have any questions about the content, you can also post them there. All of the tutors, including me, are on it, as well as sometimes other students can also provide answers and explanations as well. And it's also just an easy way to get a hold of me or Tim or any of the other tutors if you just simply add us with your question. Okay, so learning objectives. So today we're going to be talking about thermodynamics, as I mentioned. We're going to be talking about enthalpy, entropy, and internal energy. We're going to be talking about Gibbs free energy and spontaneity of a reaction. We're going to be talking about work and heat very briefly, and we're going to be measuring changes in temperature and state. And that will be solid, liquid, gas. That's what I mean by state. Okay. So without further ado, I'll move on to the content. So first, we're going to cover the basics of thermodynamics, right? And thermodynamics, as you can see here, this is an engine. Thermodynamics and different reactions, the thermodynamics of different chemical reactions is the reason that we have things like engines, any kind of motors, fridges, anything like that. All of that runs because of the laws of thermodynamics. So we want to talk about, wait, I'm sorry, I went backwards, not forwards. So we want to talk about what are thermodynamics. Well, thermodynamics refers to the changes in energy and state of a certain chemical or physical reaction. The main application for us as biologists or chemists is to track and predict changes of reactions or molecules. Like I mentioned, this is big. Thermodynamics is very important for engines and a lot of mechanical stuff that engineers or physicists might deal with. But because we're only talking about the MCAT, and mostly it's all about biology and chemistry, that's what we'll be focusing on, right? And that would involve chemical reactions or molecules. So the first and most important quantity in the universe is entropy. Entropy is essentially a measure of the randomness of a system or of the universe itself. And it's represented by the letter or symbol S. So the entropy of the universe can never decrease, right? The randomness or chaos of the universe can never decrease. It can only stay the same, or it can only increase. There can never be a chemical reaction that occurs that will decrease the entropy of the universe as a whole. And when we say universe as a whole, we're talking about essentially everything, right? Everything that we know. However, there can be chemical reactions that decrease the entropy of a small system in the universe, and that's what we mean by system. A system is just a small part of the universe. So say you had a container, right? Small glass container in which you had some chemical, that you put in some chemicals and they underwent a reaction. Well, that small container would be a system in the universe, right? And everything outside of the container would be the surroundings. Everything that makes up the universe that's not inside the container is the surroundings, whereas the system is the actual contents of the container. Okay, so there can be chemical reactions inside that container that decrease the entropy of that container, but the entropy of the universe as a whole cannot decrease. So what that means is the entropy of the surroundings, so everything outside the container, as a result of the chemical reactions inside the container, must increase entropy at least as much as the system decreases, right? In order to maintain balance. And you can see that with the equation we have at the bottom. The entropy of the universe equals the entropy of the system plus the entropy of the surroundings, right? And that's because the universe is the system plus the surroundings. So if you combine everything inside the container, everything that's not inside the container, you just get everything. Okay. Okay, so how do we change entropy? So there are many ways that changes to entropy occur in a molecule or a system. The main way is through changes in state. So for example, a gas will always have more entropy than a liquid, and a liquid will always have more entropy than a solid. And you can see that over here in the bottom right with these molecule diagrams, which I'm sure you've seen before. So if you look at this, which is a gas, the molecules are very free to move around and bounce around, and they have many different positions or locations they can be in at any given point. Because of that, there's a lot of potential for random or different assortments, essentially, of the molecules in space. That gives a very high entropy. If you look a little bit to the left, you see the molecules of a liquid. You can see they're a little bit more packed together. They can still move around a little bit around them, but to much less degree. That means that there's many less potential locations or ways they can be arranged inside of the container in order to kind of like be random. So because of that, the entropy is less. If you look at a solid, it's completely rigid, completely tight. There's no movement, it's just rotation and vibration. Because of that, very little different potential for randomness. And because of that, it will have very low entropy. And this is pretty much always the case. Solid is less than liquid, which is less than gas, for entropy at least. So another common way to change entropy is through temperature. So if you increase the temperature of a molecule, you increase its entropy, and vice versa. If you decrease temperature, you decrease entropy. Entropy has units of joules per Kelvin. So you know that joules is a form of energy, and Kelvin is a form of temperature, is a unit of temperature, I should say. Increasing the temperature increases the kinetic energy of the molecules, right? So if you want to go back to this diagram, you notice how the gas molecules are like, they have the arrows, which means they're bouncing around inside the container randomly. If you increase the temperatures, you increase the kinetic energy of the molecules, which means you also have to increase the speed where the molecules are traveling, which means the molecules will move even faster around this container, right? And that's would increase the energy, which would increase the joules of entropy, right? So if you have entropy, and the numerator of entropy is joules, and the denominator is Kelvin, with increasing temperature, you do increase Kelvin, which would make entropy smaller, but you also increase joules by an even larger amount, an improportionally large amount. And because of that, you actually end up increasing entropy, okay? Like I mentioned, entropy itself usually has units of joules per Kelvin. However, delta S, or changes in entropy, especially of a reaction or a small system, usually has units of joules per Kelvin per mole, right? And that's because most of the chemical reactions we look at are on a per molar basis, right? Okay, and I'm glad somebody asked in the chat, what is entropy? And people in the chat are answering, so that's great. All right. Another very important quantity in the universe that we're talking about is enthalpy, which has the symbol H. What enthalpy is, it's a measure of the total heat content of a system. Enthalpy is a derivative of internal energy, which has the symbol U. And internal energy is essentially just a measure of heat energy. Because this isn't a physics class or even thermodynamics like chemistry class, we're not really going to be talking that much about internal energy. That's more important, again, in physics or in physical sciences. But we will be but it is the basis of enthalpy. And the formula for this is H equals U plus PV. PV is pressure times volume, right? So since enthalpy comes from internal energy, which is a form of energy, as the name implies, conservation of energy, which is a law that we hopefully know, energy cannot be created or destroyed, just like mass cannot be created or destroyed. Conservation of energy also applies to enthalpy. What this means is that unlike entropy, in which the entropy of the universe as a whole can stay the same, or it can also increase over time, it just can't decrease. With enthalpy, or H, the total H of the universe can never change, because that would mean energy has been created or destroyed, which is not allowed. So it can't increase, it can't decrease. Enthalpy of the universe always stays the same. However, again, just like with entropy, enthalpy of a system can change as long as the enthalpy of the surroundings, so everything outside the container we're looking at, also changes. So in this case, it has to change by an equal but opposite amount. If the enthalpy of the container increases by 10, that means the enthalpy of the surroundings has to decrease by 10 in order to balance out. And this again also has an equation of enthalpy of the universe equals enthalpy of the system plus enthalpy of the surroundings. Okay, so moving on. Enthalpy is commonly used to measure the favorability of a reaction in terms of heat. So we know that for entropy, the universe always favors something that's more chaotic, more entropically favored. That would mean, for example, going from a liquid to a gas, going from a solid to a liquid, going from like a cold state to a hot state, so increasing temperatures, something like that. It favors going, essentially, mostly it favors going from a lower entropy state, so like solid, to a more entropically favored state like a gas, okay? For enthalpy, however, enthalpy measures the favorability in terms of heat rather than randomness. For example, if a reaction has a delta H, which is just a change in enthalpy that is negative, that means the reaction releases heat to the surroundings, which is favorable, right? We want the system to release heat into the surroundings. If the delta H of a reaction is positive, that means it had to have absorbed heat from the surroundings, which is not very favorable when we look at it, right? We want it to release, we don't want it to absorb. These are called exothermic, endothermic, respectively. And you can think of it this way: exo means outside, so releasing heat outside is exothermic. Endo means inside, taking in heat from the outside to yourself, taking heat inside is endothermic. Exothermic is favorable, endothermic is not favorable in terms of heat. The units for enthalpy are joules, just like with any other form of energy. However, delta H for a chemical reaction is usually joules per mole. Just like I mentioned, when we look at chemical reactions, we usually do it on a per molar basis. Okay. And there's this thing called delta H formation, which is what we're going to look at next. And this is the main thing that you'll be looking at when you have questions regarding enthalpy on the MCAT. So one easy way to find the enthalpy, the delta H or change in enthalpy of a chemical reaction is if you are given the delta H of formation of the reactants and the products. Okay, so if you look here, there are these water molecule. So we're turning methane plus O3, which is ozone, into CO2 and H2O, right? It's combustion. And we want to see how much energy does this reaction release, right? How much heat does this reaction release? Or I shouldn't say heat, because heat is a different thing. How much energy does this reaction release? How would we do that? Well, if we have this table right here that shows us the delta H information of each of these different components, right? So for example, if we have the delta H information of water, the delta H information of CO2, O3, and CH4, we can then find the delta H of the whole reaction, or Rxn, in the bottom. And the equation is the delta H of the reaction is the delta H formation of the products, or it's the sum of the delta H formation of the products minus the sum of the delta H formation of the reactants. So what you would do in this case is you would take the delta H formation of water, multiply it by 2, because again, this is kilojoules per mole, right? Give you in kilojoules per mole. So that means since we're using 2 moles of water, we'd have to multiply whatever value this is by 2. And then you have CO2, delta H formation of that. You'd add those together and then subtract the sum of these 2 delta H's. Okay, then you would have the full delta H of the reaction. And we're actually going to do that in this next slide. So please, we're going to open a poll. Second. Okay. So we're going to open the poll. I believe Tim has the power to open polls. And we will get started, but please. And remember, no calculators on the MCAT. So try to do this on your own, just on a piece of pen and paper. Okay. I'll give you guys a couple minutes.
Mark, what are we solving for?
Oh, I'm sorry. We're solving for the delta H of the reaction. Yeah, so we're solving for the delta H of the reaction. Okay, please take another 30 seconds or so to answer the question, get your answers in, and then we'll go over it together. Okay. As a reminder, these polls are anonymous. Nobody knows what you specifically put in. Okay. Okay, last couple of seconds, get your answers in if you haven't already. And Tim, if you want to close the poll and share the results.
All right, so yeah, I'm kind of curious if we gave you guys enough time or not, but we have, because not everyone responded. 75% said C and 25% said D. So maybe.
Oh, I realized I made a mistake on the poll. So does the poll? Yeah, there's no answer E on the poll. Right. Okay. So so since nobody picked answer A, could we relaunch the poll for another maybe 30 seconds or so? And if you want to choose answer E, please choose answer A, right? Since nobody picked answer A in the first place, right? You guys
Okay.
like that?
All right.
Yeah.
I'll just relaunch it.
Yeah, please relaunch it. Pick which answer you think is best. But if you want to choose answer E, choose answer A instead. Like put A in the poll as well, because we don't have an E in the poll. All right, there should be enough time. If you want to close the poll and
Yeah, we're getting some results. Okay, so more people got an answer, and so I'm going to close. So yeah, 70% said A, 30% said C.
Okay, so that's good. Or I should say the 70% belongs to E. Okay. And so I'm actually happy because the correct answer was E. It's negative 945. And again, we added these numbers up and then we subtracted these numbers from them. Just the only trick is multiply water by 2. Okay. So let's move on to the next section. Actually, before I do it, does anybody have, like I mentioned, any really quick questions about just this question or anything in general, just something very small you guys want to ask? Okay. Now I'll move on, and feel free, please always ask in the chat. We have a couple of different tutors in here that could answer that, answering questions in detail with you in the chat. Okay. Next, we're moving on to Gibbs free energy. And you see how this is a big like energy storm or whatever. And that's essentially what Gibbs free energy is it's the available energy that can do work from a reaction, okay? So if you have a chemical reaction, what Gibbs free energy measures is essentially when you use that reaction, how much energy does that reaction produce that can actually be used to do something? Again, make an engine work, fridge work, motor, anything like that. Okay. Okay. So Gibbs free energy, right? How do we determine, just ignoring that, how do we determine whether or not a reaction is favorable or not as a whole? I've mentioned whether it or not a reaction could be favorable in terms of entropy. Again, if it goes from a solid to a liquid, it's favorable. If it goes from a liquid to a solid, not favorable. And if it goes from a high enthalpy to, if there's a negative change in enthalpy, like it's exothermic, it's favorable. If there's a positive change in enthalpy, it's endothermic, it's not favorable thermodynamically. But what if it's conflicting? What if it's entropically favored, but in enthalpy it's not favored, right? How would we know that? Well, we use this quantity delta G to determine that, and delta G is the change in Gibbs free energy. Delta G is a measurement of a reaction to determine if the reaction is favorable overall, taking into account all factors as I mentioned. Some reactions have positive delta S, which is favorable, but a positive delta H, which is not favorable. So it's hard to tell whether or not the reaction as a whole is favorable without using delta G. And this may be a small point of confusion. So in terms of favorability, delta S, entropy, is favorable when it's positive and non-favorable when it's negative. Delta H is the opposite. It's favorable when it's negative, not favorable when it's positive. Try not to remember it based on the signs. Try and remember what it is, favorable or not favorable, based on what actually is happening. So try and understand it. For example, what does a positive delta S mean? Well, it means you have more entropy at the end. Sorry, that's good enough. You have more entropy at the end than you started with. Entropy, you know, is what the universe wants. It wants randomness. So if you have a positive delta S, that means there's more randomness at the end than there is randomness at the beginning, which is good, right? That's what the universe wants. So we would want a positive number in order to be favorable. Whereas a negative number for delta H would mean that the reaction is exothermic. Well, if a reaction is exothermic, then it's releasing energy, and that's what's favorable. Negative means exothermic, and exothermic is favorable. Positive is endothermic, which is not very favorable. If you want to think about it again, start and finish. In delta H, if the ending energy is higher than the starting energy, that means that energy must have come from somewhere. So what that means is it came from somewhere else, and it had to have been absorbed. That's not good. We don't really want to absorb energy from other places, because that means you're taking energy away from something else. We don't really want that. We want to be releasing energy. So we want the energy of the system to be lower at the end than it was at the beginning. Okay. Next, how do we find delta G from delta H and delta S, right? So we have this formula, delta G equals delta H minus T delta S. And T is temperature in Kelvin. Okay, the temperature of reaction. This only really works at constant temperature if a reaction is at constant temperature, but on the MCAT, almost all reactions will be at constant temperature. If the delta G is negative, the reaction is exergonic and favorable. If delta G is positive, the reaction is endergonic and unfavorable. This may seem familiar. This is the same system we used in delta H. Delta H also, if it was negative, it was exothermic, and if it was positive, it was endothermic, and it was favorable and unfavorable, respectively. Delta G works in the same way. Exergonic means you're releasing. Gonic is just a word that they use to describe free energy, right? So Gibbs free energy. You don't have to like go that deep into it, but again, exergonic, exo, outside, releasing it outside, endo, inside, taking it in. Right. Looking at the simple math, even in using just this formula and what we know without even knowing anything about like delta G or anything like that, we can see that if delta H is a negative number, meaning that it's favorable, delta H is favorable when it's negative, and delta S is positive, which also means it's favorable, right? I'm going to draw it on here. So we have a negative number minus, you know, temperature is always a positive number. Temperature can be negative, especially in Kelvin, at least. In Celsius, it could be, but in Kelvin, it could have be negative. We take temperature and we multiply it by a positive number. So we take two positive numbers and we multiply them together to get a positive number. A negative number minus a positive number, that's always going to be a negative number. No matter what the numbers are, it's always going to equal a negative number. And we know that when delta G is a negative number, it's also favorable. So if delta H and delta S both favorable, delta G is also always favorable under any conditions, right? If we look at it differently, delta H is positive, so it's not favorable, minus T is always positive, delta H is negative, which means it's also unfavorable. Positive number times a negative number is a negative number. When you do double negative minus a negative number, it's actually two positive numbers. So it's a positive number plus a positive number. Well, that's always going to give you a positive number. No matter what the conditions are, no matter what the numbers are, it's always going to be, delta G is always going to be positive, which is unfavorable. The problem comes in what if delta H is positive minus, and we say T is also, S is also positive. T we know is positive, so it's a positive number minus a positive number. Well, that depends. So if it was 5 minus 3, it would still be positive. If it was 5 minus 10, it would be negative. So the rule in this case is that if they're conflicting, if the delta H and the delta S are conflicting in whether or not they're favorable, the rule is if temperature is very high, that means delta S wins. It will choose, delta S is what determines whether or not the reaction as a whole will be favorable. If temperature is low, delta H is what wins, or it will be what determines whether or not the reaction is favorable. And we can see that here. So like so this positive number in this parentheses is made up of T times S. If we know that S is positive and H is negative, right? If T is a huge number, it's like, if we pretend that delta H is like, say 10, right? Minus some two numbers. Let's say S is 5. S is 5. So it really depends on what the T is, right? If the T is a big number, like 5, well, that's 10 minus 25, and the resulting is negative, right? And negative is favorable for delta G, and delta S was what was favorable in this reaction. Delta H was not favorable. It's delta S that was favorable. Because the temperature was high, delta S was favorable. Delta S determined what the favorability of the whole reaction was. If we say that temperature is low, say 1, so pretend it's a low temperature 1, right? 1 times 5 is 5. 10 minus 5 is a positive number. Because temperature was low, delta H is what was the deciding factor, and delta H was not favorable, so the reaction as a whole would be not favorable. Okay, so at high temperatures, you look at delta S for favorability of delta G. For low temperatures, you look at delta H for favorability of delta G. Okay, units for delta G are usually, again, joules per mole, because it's a form of energy. It's energy and it's for a reaction. So again, per molar basis. Okay, right, and there is a chart for Gibbs free energy. So, so there's a chart for Gibbs free energy that we put in the chat. Please look at that, memorize it if you want to, but you can really like think it out, kind of understand it. If you do enough practice now, by the time you get to the MCAT, you'll have that chart, like you'll be able to do that in 2 seconds. You don't have to memorize anything. Okay. All right. Let's move on. Okay. Well, I guess that there goes the answer. I didn't mean to click it twice. But just look at it for a little bit. We don't have to do a poll because I showed you the answer. But just think about it for a little bit and see what you would have chosen if you didn't know the answer. Try and like think it out and see why a certain answer might be the correct answer. Right? Okay. I'll give you guys maybe a minute or so, or 30 seconds or a minute or so. I don't think we need a poll for this one. I think we can just try it on your own. Okay. Hopefully everybody's had enough time. I'm gonna see, well, the answer, as I showed before accidentally, it's A, it's exothermic. But I want to go over this and I want to explain like exactly why this is. So what do we know? Well, we know that delta S is negative. We have a negative delta S. Because negative entropy is negative delta S. Negative enthalpy is negative H as well. I'll actually erase that here. It's a little bit confusing. Right, we know that H is negative, S is negative. Okay. What does this tell us about the reactions, right? It's exothermic. We know that H is exothermic because it's negative. And we know that that's favorable, right? That's good. Favorable. I put a check marks to show it's favorable. S, however, is negative, which is in terms of entropy is not favorable, right? That means that the energy at the end is less than the energy the entropy that you started with, which is not good, right? So that's an X. What does this mean for G, right? And endergonic and exergonic refer to G. Well, it means it depends. If the temperature is high, delta G would also be if temperature is high. Here, I'll draw it out. Temperature is big. It's a high temperature. It's an arrow pointing up. You would look at what the S says, right? You would look at the entropy, and the entropy is not favorable. So what that means is delta G would be positive, which is not favorable, right? If instead temperature was low, we would look more at delta H, and delta H is favorable, so delta G would be negative, and it would be favorable, right? I'm not going to draw it all out, but hopefully you understand by now. So what does that mean for this in terms of this question, right? Well, we don't have enough information. We don't know what the temperature is. We don't know the numbers, right? So we don't actually know if it's exergonic or endergonic. We can't figure that out because it could go either way, right? Well, exothermic or endothermic, we can figure that out. We know that it's exothermic because delta H is given to us and it's a negative number. A negative delta H is always exothermic, right? Because it has less enthalpy at the end than what it started with, or less energy at the end than what it started with. What does that mean? Well, that means it had to release some energy to the outside, right? Exo had to release out. Okay, so with that we have A. Hopefully that makes sense. Okay. A little last quick thing about delta G before we move on to a different topic. So there actually is a relationship between delta G standard and KEQ, which is the equilibrium constant. We haven't really covered equilibrium yet, but we will soon. And if you guys already know from previous courses, or we actually covered equilibrium in a different program before, maybe about a month or so ago, or 2 months ago. But if you know what equilibrium constant means, then this may make sense to you. And there's a relationship between this and delta G standard. Delta G standard, which has this like little degree sign on the top, is different from delta G. And we'll cover those differences a little bit later, but just know that they're a little bit different. The formula for delta G standard is negative RT ln K, where NK is KQ, at equilibrium, where R is the gas constant, 8.314 joules per mole Kelvin, right? And again, if you want to actually look at units, which I always highly recommend doing, you know that R is joules per mole Kelvin, temperature is Kelvin. If you multiply R by T, Kelvin in the denominator and Kelvin in the numerator cancel out. And then you're just left, KQ is unitless, it's a unitless number. So whenever it adopts whatever units, it's essentially like a constant like 5. So if you multiply something by 5, the units won't change. And what you're left with for R is joules per mole, which is the units for delta G, right? There's also the formula delta G standard equals negative RT ln Q. When the system is not at equilibrium constant K can only be at equilibrium, right? That's why it's the equilibrium constant. When it's not equilibrium, use Q instead. It's very similar. It's not extremely important to know that if it give you a Q, you're probably using this number, right? A big Q, capital Q, right? You're probably using this equation. That's really the only thing big Q is ever used for, in the MCAT at least. Okay. And like I mentioned, there is a difference between delta G and delta G standard. Delta G standard is the delta G of a certain reaction at standard conditions, STP, standard temperature and pressure. Standard temperature is 25 degrees Celsius or 298 Kelvin. Standard pressure is 1 atmosphere. And I'll have this all on the slide in a bit. Usually in biology, we don't do things at STP because the body is not 25 degrees Celsius, it's 37 degrees Celsius. So we don't use delta G standard in biology. In chemistry, we do because most chemical experiments are done in STP, right? And standard temperature is like room temperature. It's like 25 degrees is what room temperature is. Right, so like I mentioned, delta G depends on temperature. Delta G standard is always at 25 degrees Kelvin, whereas delta G not standard is the delta G at whatever temperature you're looking at. If you're looking at 37 degrees Celsius or I believe it's 313 Kelvin, that would be the delta G would be different than the delta G standard of a certain reaction, right? And again, this will all be on a slide and I'll cover this in a bit. First, I want to go through this question, right? Please take a little bit of time, really think about it. I know this is a really hard one. Takes a bit of time, a little bit of thinking. Highly recommend using pen and paper, right? So I'll give you guys maybe 1 or 2 minutes for this. Please work it out. Try and find an answer. Poll should be going up right now. Okay. If you guys want to take maybe another 30 seconds or so to answer the question. I know this is a little bit complicated and we'll go over it in depth, so don't worry about it. Just please try your best. And remember, this is anonymous, so. Okay, last couple of seconds. All right, Tim, if you want to stop the poll and share the results.
Yeah, sure. So 11% said B, 22% said C, and 67% said D. And I'm going to share them.
You said 67 is D, right?
Yeah.
Oh, that's the correct answer. So that's great. Let's go over this in a second. Sorry, how do I get rid of this annotation? Okay. So what do we know? We know what delta G standard is, right? And it's negative 30 kilojoules, right? What expression gives the ratio of ADP to ATP? So what is that, right? That may be throwing some of you off. Well, if you remember what what KQ is, okay, I'll try K, right? And it's the concentration of products products. Sorry, it's a little bit hard to write on it. A little bit hard to write on a mouse. But yeah, products over concentration of reactants, right? I'll just leave it as R, but that's concentration of products over reactants, right? What are the products and reactants in this case? Well, the products are ADP and phosphate alone. So there's actually 2 in the numerator, but they told us the concentration of phosphate is 1. So multiplying anything by 1 is just itself. So we can actually just eliminate that, right? So it's just the concentration of products. The concentration of products is just the concentration of ADP. Concentration of reactants, well, water we always get rid of because water doesn't really matter. And if we have it in the reactants or on the product side, we just get rid of it. We don't do it when we're calculating KQ. So essentially what K is just concentration of ADP to ATP. Well, that's what the ratio, right? So what they're asking us to find is actually K. So K is the unknown, right? And they give us RT, which is 2.5. Well, we have an equation that we can use, right? G equals RT ln K. We know that RT is 2.5, so we can actually solve it. We don't need any temperatures, we don't need any R's, we don't need anything. 2.5 times ln K. And we know that this is negative 30. We do negative 30 divided by 2.5. We get 12, right? 2.5. We get 12 equals ln K. And I gave a whole thing when I gave this lecture before on how we would solve this, right? Some of you may not know how to do logs or ln. Well, think of it just like you do multiplication and division. This was 2.5 times ln K. So to get rid of this 2.5, what you had to do was you had to divide both sides by 2.5, right? Division is the opposite of multiplication. If you divide both sides by 2.5, do the opposite operation, you can just get rid of this 2.5 to get to 12. Well, ln K, you want to get rid of the ln. So what would you do? The opposite operation of ln is e to the power of. So what you would do is you do e to the 12th, e to the 12th equals e to the ln K, right? So ln K. Well, e and ln are opposite operations, just like multiplication and division are. If you multiply something by 5 and divide it by 5, nothing happens. You can just get rid of both those. Same thing here. Take e to the power of something and ln of that thing, you can just cancel them out, right? And what you're left with is just k equals e to the 12th. And that's how you get the answer, right? Okay. Oh, and I see in the chat. Yeah, okay. So yes, I might have misspoken. Yeah, STP is my bad. STP is 273 degrees Kelvin. Standard conditions, which is actually what we're using. We're not using STP, we're using standard conditions for delta G standard. That's 298, right? But I'll answer the questions regarding this, but I just want to clarify that I misspoke. It was standard. It's not STP, standard temperature pressure. It's standard conditions, which for delta G standard, which is 298 degrees Kelvin. I'm sorry, that was my mistake. I misspoke. But yes. And like I mentioned, STP is 0 degrees Celsius, which is 270 Kelvin, but standard conditions is 25 degrees Celsius or 298 Kelvin. And usually we'll always be using standard conditions. That's kind of why I guess I got those two confused, because you very rarely, especially in like the MCAT, especially for the MCAT, you don't use STP. SPE, I think, is only really used for gases. But delta G, like very few things with gases. Standard conditions is what almost is always used. Sorry about that. But yeah. Now going back to this question, somebody asked quickly in the chat. Yeah. You had, you know, that delta G is 30, negative 30. And you know that this was 2.5. So you just divided 30 by 2.5, right? 30, you just divided 30 by 2.5 and you get 12. Any other questions about this? Oh, and I'm sorry, I actually negative RTL and K. So that's why the negatives cancel out. It's negative RTL and K. So it's negative 30 divided by negative 2.5 is 12. Yes, this is the last question and I'll move on. RTL and K is used to help find Gibbs. Yes, or in actually this case, we used Gibbs to find K. But yeah, it's an equation. What it means conceptually is that the free energy and the equilibrium constant are related. That's what it means conceptually. We already knew that it's related by T. Gibbs free energy depends on T, on temperature. We knew that from the equation we had before. The delta G equals delta H minus T delta S. We knew it was dependent on T. Now we also know that it's proportional to K, to the equilibrium constant. Equilibrium constant and G are related. This is kind of a small link between kinetics and thermodynamics, but we'll really cover that more later. Yeah. Okay. Moving on. Again, if you have any more questions, please feel free to ask in the chat, and we have TAs. Tutors watching that. Next, I want to talk about heat and temperature. So usually we think of those as the same thing. Heat and temperature are like in everyday life. We would think of those as the same thing. They are completely different in physics and chemistry and biology. They're very different values. They represent very different things. One of the main things that we want to talk about with heat and temperature is state changes. As you can see, ice cubes melting. That's like a very big topic in heat and Q, right? And, the next slide. Heat is actually represented by the letter Q, and it's a lowercase q, right? which is a little bit which is completely different from the uppercase Q, which we talked about before. So don't get those two confused. And delta T, which is just change of temperature. Okay. A very common formula you may be asked about it on the MCAT is Q equals MC delta T. Most people say Q equals MCAT because the delta looks like an A, right? So Q is heat, M is mass, C is heat capacity, and T is temperature. In this case, temperature could be Kelvin or Celsius. It doesn't matter because to get from Celsius to Kelvin, you add 273. So if you look at the math, it doesn't actually matter if it's Celsius or Kelvin. The difference in the temperature is going to be the same, whether it's Celsius or Kelvin. Yeah. C is a measurement specific to each substance, and it determines how much heat is actually required to increase the temperature by 1 degree, right? And this can be 1 degree Celsius, 1 degree Kelvin, they're the same again. It is in units of joules per gram times Kelvin. Again, I use Kelvin here. Could be Celsius. It's the same. So essentially, it would be different if you did Celsius versus Kelvin. The number would be, I think, a little bit different. But it's like you can use either, right? You don't have to convert all the time. Depends what they give you and what units. It would be easier, right? So what this number actually means is, and you can look at this in the units, if you had 1 gram of, say, any substance, say like metal, some kind of metal like an iron ball or a rubber ball and like a plastic ball of the same size that weighed 1 gram exactly, all 3 of them, how much heat would you have to apply, how much energy, heat is in the form of energy, how much energy would you have to apply to each ball to get it to increase by exactly 1 degree in temperature, right? And this can be 1 degree Kelvin or Celsius, and that determines heat capacity. A number that has a high heat capacity would be something like water, right? Water doesn't change its temperature very easily, right? You need to apply a lot of heat energy to water in order to get it to change temperature, right? And you can look at this compared to something like a metal, like iron. You can heat up iron very, very easily. And that's why it has a very low heat capacity. You need very little joules of energy to get it to increase by 1 degree, right? So if it had, say, a heat capacity 5 times lower than water, if you apply the same heat or the same heat or the same energy to a piece of water and a piece of iron, the iron would go 5 times higher. It would change the temperature 5 times as much as water, right? It would change the temperature much more easily. You can get this from the name heat capacity as well. How much heat can this substance hold before it changes temperature, before it gives up and changes temperature by 1 degree, right? Higher heat capacity can absorb a lot of energy, can hold a lot of energy before it changes temperature. Low heat capacity is not. Anything with a low heat capacity is a very good conductor of heat. Again, any kind of metal or anything like that, iron, steel, copper, whatever. Anything that is a poor conductor of heat, water is not very good. Air is very, very bad. So something like an air like substance is very bad for conducting heat. So it has very high heat capacity, right? And like I mentioned, Q is measured in joules, right? Okay. Next, I want to ask, if the heat capacity of water is 4.18. If anybody wants to know, I wanted to ask if anybody would be able to tell me in the chat, actually, and I want to ask the chat this. We don't have a poll question. I just want to ask, some people would know. If you have a pot of boiling water, do you know what the temperature of the water is? So if you say you had a pot of boiling water and you boiled it for 6 hours and you had a huge pot and you were boiling it for 6 hours, do you know what the temperature of the pot, of the water inside the pot would be? If you were boiling it for like 6 hours, right? right? Okay. So a couple of people are saying 100 degrees Celsius, and that's exactly right, right? You would think that you have the pot on for 30 minutes of boiling water. The water starts boiling. Say it reached 100 degrees, because you know that's when the water starts boiling. You keep it on for another hour. You added in a lot of heat, right? So you'd think the temperature would increase, right? You kept it on a fire for a very long time, right? And from it was boiling, but actually it wouldn't change, right? If you have a pot of boiling water for 30 minutes on a heat stove, or if you have it for 6 hours on a heat stove, the temperature of the water doesn't change unless all of the water is gone, unless the water all boils out, right? As long as you have the source of water, it'll always be 100 degrees Celsius. And we're going to explain why that is right now. So if you see this diagram, on the x-axis, there's energy. On the y-axis is temperature. If you start at point A, so solid, say like ice. We had a very low temperature, we had ice. You put it on like some kind of heat source, like let's say a stove, right? And then you apply the energy, turn on the stove, you apply the heat or the energy from the stove onto the ice. As you expect, the temperature of the ice would rise gradually, slowly. That would get us this blue line up until point B. Then the ice would reach 0 degrees Celsius, which is the melting point of ice. And then at this point, it would stop raising temperature, and you would go into this red area, the phase change, which is called melting. During this phase change, you can keep the stove on, and it will still be producing heat, and it'll still be transferring heat into the ice, but the ice wouldn't change temperature. It would remain at 0 degrees Celsius. Where would that energy be going? Well, that energy would be going into actually melting the ice, turning the ice into water. Ice can't just turn into water on its own. It needs a source of energy, like an outside source of energy to do that, right? So if you notice that the red line, all of the ice would be slowly melting. At this halfway point in this red line between B and C, halfway, half of the ice would have melted into water, half of it would still be ice, half of it would be water, right? Then you progress further and further, and then by the time you reach point C, all of the ice will have melted into water. Once you no longer have ice and you have only water in the liquid state, any additional energy or heat from the stove that you add onto it would just increase the temperature of the water, right? Because the water is already there, it's already water, it's not ice anymore. Now adding heat or energy to it would raise the temperature rather than change state. Okay, then you reach point D, which is 100 degrees Celsius for water, right? The boiling point. Your water starts to boil. This red part, again, would be the phase change. You keep it on the stove, and then all of the energy from the stove, all of the heat would go into changing the water into a gas. None of it would go into increasing the temperature. That's exactly why if you have a pot of boiling water, no matter how long you keep it on the stove, as long as you have water in the pot, it will always be 100 degrees Celsius, right? As soon as you run out of water, the pot will, all of the food that's in the pot, let's say you have like a potato in there, all of the heat would be transferred onto the potato and it would burn because it's not temperature controlled anymore at 100 degrees Celsius, right? But as long as you're in this red zone of having water in the pot, all of the energy from the stove and all the heat would be going into changing it to gas form, any remaining water into gas form. Then once you reach point E, all of the water is turned into gas. Then you add more heat into the gas, and the gas will increase temperature again, right? And you eventually get to point F. Okay. And I wanted to ask you guys actually, what do you think? So we had, say, water. Like, go back to my example of a boiling pot of water. We have delta H, delta S, and delta G. At the boiling point, 100 degrees Celsius, do you think, so at this area, this red area, do you think water that's has just begun boiling would have a positive or negative delta H, a positive or negative delta S, and a positive or negative delta G, the transition of water into water vapor or gas when it's boiling at the boiling point, which is 100 degrees Celsius. If you guys want to put the answers in the chat, this is the full question. Just so first, let's start with delta H. Do you think you would have a positive or negative delta H to go from water to gas at 100 degrees Celsius? Okay. A couple of people put in positive delta H. Okay. And okay, I agree. It will be a positive delta H. So how did we know that? Well, I just told you that in order to go from a liquid to a gas, you actually need energy input, heat input, right? You need to keep the stove on for it to provide heat and energy to the water. Otherwise, you turn the heat off, you turn off the energy supply, it just stops boiling, right? This transition stops. What that means is that in order for the reaction to proceed, you actually need an energy input. You need it's endothermic, right? You need to absorb energy. Endothermic reaction always has a positive delta H, right? A positive reaction always has an endothermic reaction always has a positive delta H. We know that this is endothermic because it has to absorb heat. It's positive. Now let's see with S. Do you guys think it would be a positive or negative delta S, the transition from water to water vapor? Okay, so this one's a little bit more mixed, and let's see. Okay, so this one's a little bit more mixed. Some people are saying positive, some people are saying negative. The correct answer is actually, it would again be positive. And let me explain. So we know that gases always have more entropy than liquids. You can think of it this way first. The end result on the right side is the end result. It's gas. On the left side is the initial. So we'll keep it like this level. Sorry, this is the end. This is the end. This is the beginning. The entropy levels. Gas is always higher than a liquid, right? You know that the entropy of a gas is always higher than the entropy of a liquid. So the end result, the ending entropy is higher than the initial entropy of a liquid, right? Delta S is the change. The change was by this much, right? If I had that much, the change is by this much, and it's in the positive direction, right? The ending is more than the starting. If the ending is more than the starting, that means you had a positive change. That means you increased by a positive amount, right? We also know that unlike with enthalpy or H and G, enthalpy and Gibbs free energy, a positive delta H is actually favorable. A negative delta H is not favorable, right? We want more entropy at the end. We want a higher S at the end. So we want a positive delta S, right? We always know that, again, a gas is always more entropically favored than a liquid. So it would have to be positive, right? And going from a solid to a liquid, it would be the same thing, right? Delta H would be positive, delta S would be positive. Now, we know that delta H is positive, delta S is positive. Do you guys have an idea of what delta G would be? And I'll explain this all again because we're almost at the end. So I'll explain. I'll go more in detail. But do you guys know what delta G would be right now? If we want to move on from this a little bit, in the chat. Okay. And I think it's an agreement, at least for delta G, it's an agreement. And I actually like the way that somebody put it in the chat, negative at high temperatures. And yes, so because they are conflicting, delta H is not favored, delta S is favored. They're conflicting. Like I said, at high temperatures, delta S wins, or delta S gets determined favorability. Since delta S in this case is favorable at high temperatures, delta G will be favorable or negative, whereas at low temperatures, delta S would lose and delta H would win, which is, it would be unfavorable, so delta G would be not favorable. And that's what actually the melting point is. The melting point, or the boiling point, I should say in this case, because we're going from liquid to gas, the boiling point is the temperature when S starts to win out over H. The boiling point and the melting point are the lowest temperatures in which delta G is negative, right? If you go even 1 degree lower than the melting point or the boiling point, delta G is either 0 or it's positive, right? It should be positive, right? Once you reach the boiling point or the melting point of anything, that's when that's the first temperature, that's the lowest temperature that delta G is negative, right? That's why once you reach that point, it starts boiling or melting. Okay, so this is a good exercise. I'll go over it again a little bit if anybody's still confused, especially about delta S. Okay, and the same thing would apply if I asked you about the melting point instead of the boiling point, going from a solid to a liquid. Delta H would be positive, delta S would be positive, delta G would be negative at the boiling point or the melting point. If you go lower than the boiling point or melting point, delta G is positive. Okay, I'm gonna cover this and then I'm gonna move on. I think this is one of the last slides. There's just some important takeaways that I wanted you guys to know. So today we've been talking about thermodynamics. Thermodynamics only tells us if a reaction will or will not occur naturally. Does not tell you the speed of the reaction. That is for, it's actually not kinematics, it's actually kinetics, as this typo. It's not kinematics, it's kinetics. Those are a little bit confusing. Kinematics is, kinetics. Kinematics is what we covered last week. It's like the projectile motion, it's the physics thing we covered last week. The velocity, acceleration, projectile motion, things like that. Kinetics is for reactions, okay? There's delta G and then there's delta G standard, which I talked about earlier, which just means that it's at, again, this is a STP, it's standard conditions, right? Standard conditions, right? Which is at 298 Kelvin and 1 atmosphere. Be careful because delta G does change with temperature. So pay attention to what temperature you are given. The same can apply for entropy and enthalpy. Enthalpy, I believe we assume it doesn't change with temperature. That's how the MCAT does it. Most of the time you assume it doesn't change with temperature because it's small changes. But S, you do assume it changes with temperature. From delta S standard to delta S, it could change, right? Sometimes you may actually even assume that I think it doesn't change with temperature in certain cases, right? They'll tell you in the question for sure. But delta G definitely changes with temperature. From delta G standard, to pay attention to what the temperature they give you and which value they give you, delta G or delta G standard, right? And the equation for getting between delta G and delta G standard is this one. Delta G equals delta G standard plus RT ln K. We actually have seen this formula before, right? We've seen, let me clear this. We have seen the formula of, it was this one, right? Delta G standard equals negative RT ln K. Well, if you actually look at it, because that was at equilibrium, right? Delta G at equilibrium, you know, is 0, right? If it's negative, it's favored in the positive direction towards the product. If it's negative, it's favored in the forward direction towards the product. If it's positive, it's favored towards the reactant, towards the left side of the reaction. If it's 0, it's favored both ways. It's actually at equilibrium. So whenever you see an equation of equilibrium, know that delta G is always 0 at that point. Delta G standard at that point might not be 0. Delta G standard is completely different, right? But delta G is 0 at equilibrium. And you know that if you just put this to the other side, since this is 0, you just move this to the other side and you have delta G standard on the right and then negative RT ln K on the left. And that's how we derive that equation actually. But if you're given, even if you're given a non-zero value, as long as you know the K, as long as you know the delta G or the delta G standard, you can always find the other variables in that equation, right? And that you can always transfer that for going from delta G to delta G standard. Like I mentioned, that was the last slide. Thank you very much for coming. I will stick around for a bit, for about 10-15 minutes to answer questions about this lecture as a whole. I didn't want to stop the lecture midway through the question, because for those who didn't need them answered. Office hours are every Sunday, 8:30 to 10:30. If you have any specific questions, passages, problems, topics, anything that you're confused about, please, I'll be there. A bunch of the other tutors will be there. We'll all be able to answer any questions. We will try and get this PowerPoint and recording out to you. If you don't find them in the next day or so, they will be posted on the in the group me though, so for sure look out for that. Email me. I'll send them to you if anything. Yeah, I do post the lecture recordings, like I mentioned, in the group me. This is the same link for the office hours. The link to the group me, I'll actually share that with you right now. I'll put it in the chat, because it is in this PowerPoint, but here, I'll put it in the chat. And whoever sorry, I put that in the chat. Here, I put myself for some reason. I'm not sure if it was somebody here or if it was just something on my end. The current recordings are found on the Socratic Med YouTube channel. Yeah, it's somebody Janelle posted in the chat. Okay, anybody have any questions? Do you want me to go over specifically what I asked this? Does anybody want me in the chat to go over anything in particular? Do you want me to go over why delta S was positive in that example I gave with the water melting? Oh, okay, first I'll answer this question. For the equation with e to the -12, for sure, let's go back to that. Yeah, and please, if you have questions, please raise your hand like that, and I'll ask you first. But first, I'll answer this question. So, how do we know to use e to the 12? How do we know which equation to use? Well, you have to in any question, physics, chemistry, you have to know what they give you, and then you have to think, which equations do I know use these variables, right? They gave you delta G. They gave you RT. From that alone, you should be able to think delta G equals negative RT ln K, right? Because the only variable you're missing is K, right? Now, you have to also ask yourself, what are you actually looking for in this question? Is it actually K that you're looking for, that they're asking you for? What is the variable they're actually asking about? Well, they asked you for the ratio of ADP to ATP. ADP is the product, ATP is the reactant. So they asked you what is the concentration of P, I'll just call it products over reactants, right? And ratio, you know, is just division. So like this, division. They told you the concentration of this product is 1, so you can get rid of this. You know, water you can get rid of for whenever you're calculating KQ. So you just get rid of this. Essentially, when you're looking for K, K is equal to concentration of ADP to ATP. Which expression gives the ratio of ADP to ATP is what they're asking you for. You know those two things are exactly the same. So what they're actually asking you for is K. Which equation do you know that relates G RT well, you knew it was this one. Delta G equals RT equals negative RT ln K. Right? And then from there, you just have to, out of these 4 variables, 3 of them, only 1 variable, 1 equation, you can solve it using algebra. Sure. Okay. Lily, you raise your hand if you have a question.
Yes. Could you go over the delta G phase change from liquid to gas, please, again, because I'm not understanding. I think why it was negative or.
Right. Okay. Well, any reaction that has a negative delta G will happen, right? And you know that at 100 degrees Celsius, water will turn into gas, right? Is that so far good? If it's a negative delta G, it will happen naturally. Water to gas will happen naturally. So it should have a negative delta G. Just from that, you should be able to get it. But something that has a positive delta G, it won't happen on its own unless you specifically there's very specific cases in which you couple things together. That's like very more in depth. But essentially, what you want to know is that a positive delta G won't happen naturally, right? When you have water at 50 degrees Celsius, it won't turn into gas. Like it won't just randomly turn into gas. That's because it has a positive delta G, right? If it had a negative delta G, it would turn into gas. At 100 degrees Celsius, it does have a negative delta G. It does turn into gas. Okay.
Okay. Would that go for solid to liquid as well? Because
exactly.
Okay.
Yes.
Yeah.
It'll be
that
exactly
makes sense.
Yep.
Okay.
And it works in the opposite direction too.
Thank
Liquid to solid. Yeah. It works in the opposite direction as well. So if you had a liquid and then you lower the temperature to 0 degrees Celsius, if you had a water and you lower the temperature to 0 degrees Celsius, the transition of liquid to solid would actually be have a negative delta G as well.
Okay.
If you lower the temperature enough, yeah.
All right. Thank you.
Okay. Okay, so let me go scroll up in the chat just to see who else has any questions. Okay. Did somebody ask exergonic versus endo? Okay. Yes. So somebody asked exergonic versus exothermic. Exothermic has to do with the release of heat. Exergonic has to do with the reactions variable. Yes, it's true. Exothermic relates to delta H. It was to the enthalpy, right? Negative delta H or positive delta H is exothermic or endothermic. Delta G, which is Gibbs free energy, relates to exergonic or endogonic. Sorry, exergonic endogonic is for delta G, right? And you can think of it spontaneity, whether it's spontaneous or not. Delta G, that's like the main use we have. Technically, it's not the actual use. That's not why exactly why it was created. Delta G. It's not. I think his name probably was Gibbs who created this energy, this term. But that's not the actual use he had for it. The actual use for G is it represents the amount of exothermic represents how much heat is actually released by a certain reaction, or how much energy is actually released. The delta G is more with the amount of energy and how much the energy release can do work. So that has to do with physics. It's like engines and motors and stuff like that. When you have a reaction in a motor, how much work can that reaction actually do once it undergoes? We don't have to know that because we're going from pre-med. We don't have to know that. We use it only for really determine if it's spontaneous or not. That's our main use for it. Yeah. does that answer your question? So exothermic, so thermic represents delta G, it relates to delta G, or delta H, sorry. Thermic is for delta H, gonic, delta G. Anybody else with any questions at all? If you put them in the chat and I missed it, please just put them again, just copy and paste them again, or raise your hand and just ask.
Hi, just one more time. Positive delta S is more favorable, but a negative delta H is also more favorable.
Exactly.
Okay.
That's exactly it. However you want to make sure you know that. If you want to just memorize it, if you want to kind of understand it and think about it that way, just by understanding it, like the broader concept, it's up to you. But just you do have to know that positive delta S is favorable, negative delta H, negative delta G is favorable.
Okay, thank you.
Yep, sure, no problem. Any other questions from anybody before we wrap up? And yes, for everybody who's still here, we do appreciate any feedback, positive or negative, for these lectures. If there's anything you like, anything you didn't like, maybe I went too fast, maybe I went too slow, maybe you liked having questions throughout the lecture, maybe you like it this way better with lectures at the end or questions at the end. Please let us know either way, positive or negative feedback. We just appreciate any feedback at all, right? And any way we could maybe you guys would enjoy doing it better. But if nobody else has any questions, I think we can wrap up for today. All right. Last call. Yeah, so most of the PowerPoints are based on the content outline, right? It's not exactly, so the content outlines actually has more than we have in terms of studying. Like I mentioned, we cover most of the high yield stuff. There are small topics that, like, I feel like personally I've never seen in a practice test or in a real test, or somebody else's, like none of the other tutors have really seen. So those we kind of like we don't really cover. Like, yeah, we do them on a small basis. Yeah, we focus on what we're actually experiencing on actual MCATs rather than what they say they test on. Lily, if you had another question.
Yeah, I was just wondering, how can I access these slides? Because I'd like to download them.
Oh, in the group meet, we put it in the chat before. We post after every lecture, we post the PowerPoint slides. We also have a Google Doc folder in the group meet that has all of the previous PowerPoint slides. So we did an 8-week program before this where we actually gave, this was one of the lectures we gave before, but some lectures aren't on it, but all the PowerPoints are there. If you want to go to the Google Doc, in the group me, we'll be posting this one. We'll also be posting the link to the Google Doc, which has all of them.
All right, thank you so much.
So yeah, it's all in the group me. Lectures are Thursdays, Fridays, Saturdays. Thursdays, Fridays, Saturdays, same time, 8:30. Office hours are Sundays, also 8:30. Yeah. If you can't make it to one of the days, which is understandable, recordings are there, PowerPoints are there. All right. Any other questions before we end up? Okay. If no, then thank you all for your time. Have a